Hey everyone, welcome back to the Design Review series. Today we're taking a close look at a board submitted by Yusuf El-Nady. It is a high voltage ultrasound actuation and sensing board. It's a fascinating design that handles conditioning stages across 8 channels, and it pushes out signals at 100 kilohertz. I'm joined by Beeker, and we're going to tear into the schematic. We'll also be looking at the power architecture and the critical design decisions in the PCB layout that make this board work. Let's dive in.
All right, the first thing I want to look at is the ground structure. Obviously, I'm seeing a single ground symbol on this. This is a good sign. My only suggestion would be to make sure that you have some type of protection capacitor between the fuse and the power conductor. Above there, that PS1 and 100 nano, I would make sure the 100 nano is close to pin 6. And then the two 10 mics are supplying energy to the device. And then you've got 47 microfarad, 100 nano. The 100 nano really doesn't necessarily do much at that point because the switching energies coming out of pin 4 are really going to be fairly low frequency because this has got really big transistors happening inside of it. So then there again, he's got another LED to tell him that this power supply is alive, which is kind of cool. And below that's PS3, same comments to that. You want to put the smaller value cap close to the pin, input pin, to catch all those depletion waves. I would take that pattern and apply it to all the power supplies. Pin 1 of L5 is at the top. It should be connected to pin 6 of the IC. The idea is to get the energy to be going inside the tunnel. So we would want to know what pin 1 is on L5. Inductors are pretty important and really want to have in your schematic the pin 1s be marked so that you can tell what they're oriented in, because that can make a big difference in the behavior of the system. Make sure we can tell what pin number is 1 on the inductors. You do it for the ICs, let's do it for inductors as well.
I like when power supplies and their blocks are enclosed in rectangles, and I also like to use a schematic for, like, they've done this already where they're giving more information explaining what the power supply is supposed to do, but I also want to at a glance know what each power supply is supposed to be feeding on the next page.
Wow.
Yeah,
that's a fine idea. The design I was just reviewing, they added notes about the switching speeds of the IOs and the effective lump distance. So if those notes were in the schematic, that could be used to help answer the questions that you would come up with during the layout process.
Why 1 ground versus 2 grounds versus, that's a whole can of worms kind of question. But yeah, I'm curious as to know why 1 ground is preferred versus 2 grounds. You know, what is the thinking, the thinking behind that
you have a continuous path from the source of the energy to the loads. That's easier to do with a single ground. If you create separate ground domains, then you are completely required to maintain anything on that new domain, cannot go anywhere else. Again, discrete domains, properly done, are extraordinary and very important. High voltage power domain, typically in a battery management system, you have a discrete ground for high power. For shield and chassis, you have a discrete ground for shield and chassis, but those domains cannot be violated and you are restricting your ability to route things. If you do not need a discrete domain that's separate, it's always best to just use a solid system ground.
Okay, so we're going to jump into, you want the MCU?
Yeah, let's do that.
So this looks good.
Yeah.
Also like let's jump out. I like the, where he intentionally puts everything like equidistant and even. Let me go to the receiver section.
There's another inductor. Again, the same question is you would want to know what pin 1 is on those inductors.
I like that there's this, he put some data sheet information here again. So we lines. This is the pulsar.
Schematic is pretty clean in general. You see a lot of really good things here.
Okay, I guess we're ready to leave this one. This is, 6 layers. 2 is ground, 5 is ground.
Excellent. Really good board stack. It's got 2 sets of paired dielectrics, 1, 2, 3, 4, 5, 6. Those triplets form a really good foundation for your circuit board. So that's a good thing. And let's just take a look at 1, 2, 3, 4, 5, 6 in order.
Okay, I'll turn off these layers and start with layer 1 at the top.
All right. First thing is I would want to see ground flood on this layer. I'm assuming across the top where these connectors are is ground. So let's zoom in one of those connectors. In this case, a lot of times I want to push the idea of not putting ground underneath between the pins of a connector. In this case, the center conductor is the actual signal, and the other 4 pins are all connected to ground. So there's an opening. The energy comes into this connector between layer 1 and layer 2 and moves into the space between pin 1 and the other pins out into the cable. So that's a good thing. However, there's only some vias down the middle between each of these connectors that may be an attempt to create isolation, but it really isn't. I would assume that these ground pins are all connected with wagon wheel spokes to layer 2 and 5. Unless they want this to be a discrete ground, I would flood all the layers with ground and then stitch them together with ground vias. Let's look at 2 and make sure it is solid. I didn't see on layer 1, it looked like they weren't flooding underneath components. When you do turn the flood on, make sure that you keep from having that ground flood be between the leads of the discrete components and the connectors underneath the IC. That's very well done. That's good for thermal and for connecting the ground itself. I'm hoping all these outputs from this device are routed to layer 3. So I guess while you're here, let's look at 3.
This is layer 3 here.
Okay, so this is the first major issue that I see with the board. All those pins are routed. You route from the IC to vias that go down the board stack. And if they're not going to 3, each of those needs to have at least a ground transition via. You can share them, so every pair of them can have a single ground transition via. To get from 1 to 4 or 6, you've got to have a ground transition via. Let's look at 4 and see if that's where they're routing these at.
So this was layer 6 here, the bottom layer.
Zoom in. Maybe there are ground transitions.
Yeah.
So no problem. Having 2 signals share a ground transition via is just fine. Point out something that's done well. This is exactly what you need to do when you go from 1 layer triplet to the next layer triplet. And that's again why I love a 6-layer board.
I have a question now that you brought that up. What do you think? What do you think about the routing here with I see they have the 3.3 volt pulse, and they pulled the ground together on these 2 devices and brought a trace out.
Yeah, I would put it, you need a ground via in the middle. The energy is really between layer 1 and layer 2, and forcing it to be coplanar from these pins on the device to the ground via means that you've got just the edge of the foil that are involved in moving this energy instead of the trace over the plane. So I want to get this ground reference for this IC to the ground plane on 2 as soon as I can. So right at this junction point between these 2 pins, I would drop a ground via. Then I don't have to route the ground at all.
Oh, wow.
Because I'm using ground. Ground is now on 2. So I'm taking the energy from the body of the IC into the space between the IC itself and layer 2. And then I've got pin 3, either that's if it's an input or an output. Either way, it now puts that energy in the space between the trace on pin 3, between the bottom of that trace and the top of the ground plane. Is where that energy is going to be.
That makes sense.
Bottom line is that we've highlighted some things that are done well. The schematic and these ground transition vias are a great example of what to do. And the board stack, we talked about that, which is a good example of a well-designed board stack. And the ground flooding. And I think that's probably a good review of the overall design itself.